Alright, let's get started with the project. So project 6 is going to be about linear least squares approximations, and it's actually going to be very short, so I think it will most likely be due within a week, and you can expect kind of like the same thing that we saw before with the previous projects. So this is actually still a draft, so the project that I'm going to show you, don't take it word for word. This is just the kind of project that we're given in previous semester, so I just want to use this kind of like as an indication. So for project 6, you will be provided a set of data values. You will be provided noisy data for the x and for the y coordinates. So we will create sort of like a scatter plot of that data, and we will try to do the least square approximation. We'll try to fit in what is known as the fit function throughout the data to better kind of like approximate it and cover as many data points as we can. So you will be provided the set of x and y data pairs provided in the text files. They're not particularly text files, as you can see. This is kind of like the name that they will have. They're .dat files, which if you're on a Windows platform, you won't be able to open them unless you have any sort of program that can read those file types. But if you want to implement them into MATLAB, this is sort of like the command, or into Octave, I'm sorry, this is sort of the command that you will use. You will use import data, and you will write the name of the file. As always, you have to make sure that it's on the same working directory as your code. Make sure you keep everything nice and organized and everything on the same folder. They're going to be given in a zip file. That's most likely what's going to be the case. So it's very similar as the project 4 files that you were provided for the Gauss Seidel with SOR. So each data file containing the x and y data, you are to best fit this data via the least square polynomial fits. That is kind of like what we're trying to accomplish in this project. And again, the objective is to generate a linear, a quadratic, and a cubic polynomial least square fit over the data. So I will show you how to change this. I will show you how to try different sort of polynomial least square fits. I'll probably do the quadratic and the cubic, and then whenever you submit the results that you obtain from this and the graphs and things like that and the figures, I'm not gonna probably ask you to run your code. Like if you run your code over and over and then just switch the one line of code that needs to be changed to implement a different type of approximation, either linear, quadratic, or cubic, that's kind of like what I'm going to ask. I'm not going to ask you really to implement any sort of like for loop and try different values or try a combination, like really heavily modify the code so it does this multiple times. You could, however, do something like that. You can get fancy with it, and I will show you where you could implement a different type of for loop that could accomplish this in sort of like one go. But if you just save the images, if you save the pictures as you obtain them, and the same thing with the values, the approximation of the error and things like that, and the coefficients, of course, then you should be fine. You can just submit it like that. I won't be taking any points off just because you were not able to do your code doesn't do everything in one go. So again, one of the objectives is to evaluate the function, the fit function that we will create. We want to evaluate it at a certain x value plus or minus the standard error, and we will also plot the function x over the domain 0 to 2 with a step size of 0.01. This is not really extremely relevant. As I mentioned before, the data is provided to you, and the data that we generate, the noisy data, already takes into account that x domain from 0 to 2 and the step size and all of that. So you don't really have to worry about that too much. I will, however, show you where to change some of the parameters so that we're all on the same page. And lastly, we want to calculate the R-square value of the standard error. So the next things are just going to be the formulas. There is your formula for calculating the R-square. There is the formula for calculating some of the components, the standard error. The n is the number of the data points. M is the order of the polynomial. This is what we will be changing to fit different values, to fit different, polynomials, like for example, a linear function, a square function of a quadratic function, and y bar is the estimated mean. So again, this is all there is to it for our problem. So let's move ahead, let's go into the code. So I try to make the code as big as possible, and as I go through this, guys, as I go through the lines, I want you to pay specific attention to whenever I call a function, because whenever I get to a function, that's when I'm gonna switch to the different files. So I have 3 files at the moment. I have the project 6 main, which is the one that we will be running from, as the one that we will run to obtain our results. I have the least square function, which is this one right here. The least square function will do the calculation of the coefficients for the least square. So the calculation of the coefficients for a fit function, and then the evaluation of the fit is just gonna use those coefficients, and it will create the actual function in this form, which is the y equals to a0 plus a1 times x to the first power plus a sub 2 times x to the second power. So whatever function we decide to implement, either linear, quadratic, cubic, fourth order, whatever we decide to go with, that's the shape that it will take. It will just be your traditional, very generic polynomial fit. Anyway, so I'm going to start with the first function. As always, we always start with a CLC, clear, close all, CLC, so we can clear a command window, clear to clear the workspace, and close all to close all the open figures. The first thing that I'm going to do is to import the data. This is the data that I was provided is in this form, and I can show you in the file browser. This is what I have. So you can see that it says x underscore data.dat, and same thing with the y data. Those will be the 2 files that you will be provided. So if I go back into my editor, those files, I am importing them using import data. Make sure that you put it in between quotes, and this allows me to import the data for x and y. The next thing that I'm going to do is I'm going to define the number of data points. The number of data points is just the size of the column that I just imported. This x and y, they're both given as columns. So the number of rows that I have, that will be the number of data points that I have. The first thing that I'm going to do, and this is completely optional. I just think it's very important for you to see it before we draw the line for the least square approximation. I'm going to create a figure, and I'm going to use the command scatter. Now the command scatter, what it does is it creates like a scatter plot. So the difference with plot, for example, like if I wanted to use plot and plot the x and y, is because plot actually creates it graphs the dots, but then it creates a straight line between them. It's kind of like drawing a line between connecting all the dots. Whereas scatter just does half of it. It just plots the dots on the graph, which is exactly the type of data that I have. Usually whenever you do any form of least square approximation, you have a bunch of noise, you have a bunch of data, you have data all over the place. Just imagine a very, very, very dispersed scatter plot, and we just try to fit a polynomial the best we can. So I will show it this in a second as I run it, or I think I can do it right now. I'm just gonna run it using F9. So I'm gonna highlight this area and press F9 just to show you what I'm talking about. So this is what I'm talking about. This is the data that we're importing. So you can see that it's just a bunch of dots, and we want to draw a polynomial, want to draw a line that tries to go over all of them. It won't do that. It won't be able to go over all of them, because that's what normally happens with noisy data. But we want to approximate this pattern with a function the best we can. So that's kind of like the goal. This is when we define the order of the polynomial. So m is what we're going to use to define the order of the polynomial. Now, what is kind of like confusing is that it's always m minus 1. So if I wanted to implement a cubic function, for example, for my function fit, m has to be 4, because then whenever I do the order of the least square polynomial fit, it will be n minus 1. So if I want to use a quadratic function, m has to be 3. If I want to use a linear function, m has to be 2. If I want to, again, use a cubic function, m has to be 4. In this case, for this particular example, I'm going to approximate it with a cubic function. I will go back and do it with a quadratic if I remember. But again, you can either create a for loop that uses different values of m for like 3 times. You can do this 3 times, one for a value of m of 2, then 3, and then 4, or you can just go back to this guy, and whenever you create your graphs, you can just save them and also save the output of the command window, because again, every time of approximation will give you different results for the errors. So you can just go back and change it. You don't have to submit a code that does all of that magically. Don't worry too much about that. But again, we will display the information corresponding to the least square approximation. We will display the number of data points, which as I mentioned before, will be the number of rows for the imported data. We have the number of least square coefficients. That depends on the polynomial fit that we're trying to use. Again, if we're trying to approximate it with a square function, for example, with a quadratic function, that will be a parabola that will have 2 coefficients. So it will have the coefficient, number of least square coefficients. I'm sorry, let me think this through. So if I'm trying to use a parabola, actually it will have 3 coefficients. I apologize for that. Number of least square coefficients, yes. And yes, if I'm using a parabola, I will have 2. In this case, I'm using a cubic function, so I will have my a sub 0. And so you can think of this on this form, where this one will be my a sub 0, this one will be my a sub 1 times x to the 1, then a sub 2 times x to the 2, and then as I continue increasing. So all of those things that say coefs, and that actually stands for coefficients, those will be the coefficients that I want to solve for. So this m represents the number of coefficients that I have, and m minus 1 will be the order of the polynomial that I can fit into this and to approximate my noisy data. So the first thing that I'm going to do is I'm going to calculate and display the least square coefficients. For that, I want to save them in my coefficients, and you don't necessarily have to define it as a matrix. However, it just makes more sense if you define it as a matrix, because it will be defined as this form of like a, I will say, 1 row matrix. For us to be, it's easier for us to see it, but this will call the least square function. I will pass as an input the x data, the y data, and the m value, which again, m is the order of the polynomial. So I'm gonna go into my least square code, and in my least square code, you can see that I have those values. And the first thing that I do is I pre-allocate the memory for the C and B matrices. Now this is your typical AX equals B. However, we do not solve it using Gauss elimination or anything like that. We actually just put it in a certain form that makes it easier for us to solve it. And then we use a linear solver. We use the MATLAB built-in linear solver to solve for those coefficients. You can think of this as your x, instead of solving for x values, we're solving for those coefficients. So it's your typical, I will say, it's your typical problem of just your traditional matrix problem. I'm slightly tempted to call it an eigenvalue problem, but I don't really recall it being an eigenvalue problem. So you can just think of this as we're solving the coefficients using your traditional matrix solver. So I'm going to go back to here, and then I can display the least square fit coefficients. And whenever I display those the least square fit coefficients, those will be the coefficients, which again, if I go back to this, will take this form. So I'm creating a function y of x, for example, and however many coefficients I have, those will be the value of the coefficients of my function. So then I move on to calculate the least square fit function. That will be when I use this eval fit function. So I'm going to pass those coefficients, and I'm going to pass the values of x, because again, I'm creating a function that evaluates over an x domain. So for that, I use this function, and this function again takes the coefficients, takes the x value, it creates a vector 1 to the length of coefficients, so from 1 to however many coefficients I have, and then it creates the sum of the coefficients multiplied times the x to the whatever power I'm currently working on, and that is how you create the wide function that will be the approximation across all of those values, across all of that data, the noisy data. So then I can calculate the sum of the squares of the errors. I use this function. Again, all of these equations are provided in the project down here. But if you don't want to go through them, you're more than welcome to just look at them in here and then just use them. So calculate the standard error, calculate the estimated mean, calculate the R squared. You have all of these functions, you know what variables they create. So in the quiz, if we ask you, or in the answer sheet, if we ask you for a specific value, or like, hey, what is the R square if you approximate it using a cubic function, if you approximate it using a quadratic function, all of those values, if you write the code like this, they all will be displayed, they all will be printed into the command window. So then I can display, as I mentioned before, I can display the resulting calculation. I can say the sum of the square of the errors will be given like this, the mean will be given like this, the R square value will be this one, and then the standard error will be this one. So all of this is the actual print into the command window, and I will show you in a second those values. So I can also evaluate the fit function at particular x value, which is exactly what the project called for in part A. They want me to use that function that I created and evaluate it at point 1.35 plus or minus the standard error. So that value can be changed in here. Again, this doesn't actually reflect the particular value that this project for the fall semester will want. This is subject to change, but this is something like an example, 1.35. I can instead of that, I can evaluate it at point 1.875, for example. And then I'm going to run my function, evaluate fit with the coefficients and the x value. This will take these values and create that function. So once I create that function, I can print all of the multiple values that I have. So I have evaluate the least square function at the actual point, and then the standard error, the y value, the y plus the SE, and the y value minus the SE. So this will be the evaluation of my fit function at that point plus the standard error and then minus the standard error. And this is the y evaluated, my y fit function evaluated at that x. So I will evaluate it at that x, and then I will add and subtract an error to account for, again, the deviation. So this is the last line of code, or the last segment. This will be the plot of the least square function to feed the data, and I will highlight the point that I'm trying to approximate, for example. And this will actually plot it on top of the scatter plot that I had before so that you can actually see the graph. So if I go ahead and run it, I'm going to skip those figures for a second, but let me show you the command window. So the command window will actually have a different size. I apologize for that. But the number of data points, I can see that is 40. There's 40 data points. The number of least square coefficients will be 4, and it's 4 because the order of the least square polynomial is 3. So if the higher order of my polynomial is 3, I'm going to have 4 coefficients. These are the coefficients that will go into a sub 0, a sub 1, a sub 2, and a sub 3. So again, I have 4 coefficients. The sum of the square of the errors is given as this. And then I can calculate my mean, I can calculate the R square, and I can calculate the standard error. Now, when I want to evaluate the least square fit, like the function that I created, at a particular point, in this case 1.875, I can see that the standard error is calculated. The value of the y, so the value of that fit function at that particular x, is also given, and then I can calculate that value given the standard error. So I can add or subtract the standard error to deviate from that point. So that will be this y value plus or minus the standard error. So that's also very important. Now I'm gonna go ahead and show you the pictures. Again, figure 1 was the noisy data that I had, and I wanted to approximate it. In this case, I want to approximate it with a polynomial fit of degree 3. That means a cubic function. So if I go into the result, I can see that in fact I have a cubic function that tries to go over all of the different points. But again, it is noisy data. We try to do the best we can to get as close as we can to all of the different points. And then you can see in sort of like a darker color, the highlighted point that was my point of interest, the one where I wanted to actually evaluate what is the value of my polynomial approximation at that x value. So let's say I want to try something different just for this fun of it. Let's say instead I want to approximate it. Again, I'm going to go back to line 17, and let's say I want to approximate it with a quadratic function. So I'm going to let m be 3 so that there are 3 coefficients, and then the degree of the polynomial is 2. If I go ahead and hit run, I'm going to skip the pictures just for a second. we can see how the values have changed. We still have the same number of data points. We have the least square coefficients are 3, the degree of the polynomial is 2, so it's a square polynomial. Again, here are the 3 coefficients that I calculated with the matrix problem. I have the sum of the square of the errors, the mean, R squared, all of that good stuff, all of that good information. I have X, again, the same point, 1.875. I evaluate the standard error. I evaluate my Y function, the fit function that I created. I evaluate that function at that X value, and then I add and subtract the standard error. Now I can go back to the pictures. Again, that same picture as before. That is just the plot of the scattered data that I imported into Octave. And here is the quadratic function approximation. You can see that it's a quadratic function. It does the quadratic behavior. So yeah, and you can think of it as the higher in the degree you go, the better of your approximation will be. Let's say we want to instead use a polynomial to the 4th degree. Let me run that again, and then we will see that this actually does a slightly better job than a cubic function. But at some point there's kind of like a point of diminishing return. So again, just follow what the project says. Follow these points. You don't have to worry too much about the B point, but that should be everything as far as the least square goes. So I hope that you guys find this useful. If you have any question with respect to this, I'm gonna do one more quick kind of like scan down of the code so you guys can see it, and you can always stop the video if I'm going too fast. But if you have any question with respect to any of this code or anything that I did, or if there's anything that wasn't clear, send me a message or just stop by during office hours. I believe this project will be due in a week. And yep, I hope you guys have fun. Thank you.